with just a brief reminder. We're talking about conservation of energy. And we are focusing on mechanical forms of energy, which means forms of energy that generally are based on position or velocity, mechanical forms of energy. So I want to remind us that we have some forms of energy that we've already discussed. The first and simplest is kinetic, energy of motion. This is something that an object has. Now, the thing I want to bring up about kinetic energy is that work done by an unbalanced force changes an object's kinetic energy. We talked about that before. In our examples of conservation of energy, if the energy can't be tracked to someplace else, it has to be in the form of kinetic. I'll say that again. If the energy can't be tracked into something else, then it falls into kinetic. We'll put you in the back row next time. On Friday, we talked about a different form of energy called gravitational potential. And I was rushing a bit, but I think I was pretty clear that gravitational potential is not something the object has. It's something that the object interacting with the Earth has. And the more you separate an object from the Earth while you're near its surface, you can store more and more gravitational potential energy, but it's an interaction. It requires the object interacting with the Earth. So this is not something that the object has. I want to keep reminding us that if asked about this, you should explain that this energy is something that is related to the interaction between the Earth and the object itself. That if you take away the Earth, the object no longer has this energy. It's not in the object, it's in their interaction. And this H naught is a reminder to create a reference level, to remind yourself that we're measuring the amount of potential energy relative to a reasonable lowest point in the problem. I use my cup as the example. When we talk about potential energy, we're really talking about changes. So set up a place in your problem, call that the lowest point, and then do all of your work from there. There's another form of potential energy we have not discussed, and we're going to need to, but I'm going to more or less introduce it without proof. I proved the gravitational one. I'm not going to prove this one because it does require calculus, or it requires graphing, and I don't really feel like doing that. This is elastic potential energy. It's the kind of energy you would get if you were to pull on or compress a spring. Elastic potential energy. Now, just a quick description of elastic potential energy so you have something to put in your notes. All right, so maybe I'm wrong. Elastic potential energy, there's a lot I should say about it, but it's not that complicated. So I want to add something to this that you should get into your notes, that elastic potential energy applies to any object that when misshapen will return to its original shape. That's where elastic potential energy applies. So it applies to any object that if you misshape it, if you deform it, if you change its shape and it tries to pop itself back into its original shape, elastic potential energy applies. A spring is the easiest one because it's very one-dimensional. So generally when we talk about elastic potential energy, we talk about springs, meaning I could pull this block backwards against the spring to create a different condition, this condition. Right? I've pulled the block back a distance x against the spring. And if I let go of the box, do you understand the spring is going to try and return to its original position? When it does, it shoots the block away. Well, this is another way of storing energy. Now, a spring is a simple way to envision this. So when we draw this, we tend to call this spring energy. But there are a lot of objects that obey the rules of elastic potential energy that aren't springs. A ball, when you drop a ball and it hits the ground, it compresses. storing the energy as elastic potential energy. The ball returns back to its original shape and pushes itself back off the ground. So a bouncing ball obeys the same rule. Rubber bands obey the same rule. The bow portion of a bow and arrow, right? You deform it by pulling the arrow back against the bow, and when you release the bowstring, it returns to its original shape. It applies that energy back to the arrow. So there are a variety of places where elastic potential energy is a viable form of energy. But in our problems, we would only use this if there's a clear piece of elastic or a spring in the problem. It's pretty easy to see. So all of these represent forms of mechanical energy. Two of them are the interaction between your object and something, some force or some object. So these two are the interactions, right? One interacts with gravitational fields, the other one interacts with a spring or something. So let's see how well you're able to apply what we talked about on Friday. I'm going to set up what I hope is a simple question. It was not simple in first period, but I'm hoping it's simple here. All right. This is our starting problem. This is the problem I'd like to kind of practice. This is supposed to be a repeat of what we did Friday. And my expectation is that you should be able to do this with very little difficulty if you just copy what we did on Friday. Now, in this problem, I'm going to release the car at the top of this first hill. Release it. That's suggesting that at the top of the first hill, its velocity is 0. I would like you to tell me how fast the car is going at A, B, and C. I want the velocity at A, B, and C. Let's assume for this particular example that there is no friction or air resistance acting in the problem. That creates the conditions for conservation of energy. Because there's no friction and there's no air resistance, there's no external force acting on the system except for gravity, a conservative force. And let me remind you, gravitational potential energy is path independent. So it doesn't matter that this is a curved path. All you need to worry about are the places in the problem indicated to you. Now, I don't know if you can do this or not. I will put the answer to B. That'll let you know whether you're doing it right or not. All right? Try it. Try it to see what you can do. All right. Now, look, I understand we went through this fast on Friday. So if you're having difficulty, or if you full blown just haven't been here for a week and you didn't watch any of the work that I did posting videos, trying to keep you up to date, which I'm not even sure why I post them, but this is not particularly tough. With conservation of energy, you compare points in your problem. It's pretty simple. So you need to pick 2 points in the problem to compare. It's best to pick 1 point that you know information about. And I think we know information about this point in the problem. And when I say no information, we're talking about energy. How many forms of energy do we have to work from? Right at the beginning of class, I told you, gave you a list even, and named them. That's right, there are 3. So there are 3 possible forms of energy that you should ask about in every portion of the problem. And like I said, if you didn't know how to do this, I would encourage you to write this down. This isn't hard though. I'm going to compare the start of the problem with B. And so right now I'm making a novice guide to doing this. I'm telling you everything you have to do, but I was hoping you could conjecture your way out of it on your own. If not, you should pay attention. There's 3 forms of energy. Energy doesn't have direction, so I can just add them up. And I'm going to set the result of this equal to the result of that. It's that easy. But you have to figure out which forms of energy exist in each part of our problem. So I'll give you a series of simple questions to ask. You'll notice I wrote these in the same order: UG, UE, and K. Gravitational potential energy. Ask yourself, is the object above the lowest point it's likely to attain in the problem? It's a pretty easy sentence. You get to pick what you think is the lowest point. I'm going to pick this. I think that's the lowest point, right? The bottom. I'm sorry. Here, the bottom. That's the lowest point to me. Well, the car starting 3 meters above the bottom, I think it's above the lowest point. I'm putting a 3 in for the H. Yeah, I might know other stuff too, but MGH is what we're talking about here, so I'm hitting the high point. Is the object, this is question number 2, is the object pressed up against a spring or a piece of elastic? Then that's a big 0. There is no form of elastic potential energy. So if you see no spring, no bow and arrow, no piece of elastic, then you probably don't have elastic potential energy. Is the object moving, or is there residual energy that's left over for the object to have kinetic energy? I tell you that the object's velocity is 0 at the start. So there is not any kinetic energy. I evaluated the start of the problem. Now I'm going to evaluate part B. At B, is the object above the lowest point in the problem? Yes, it is. So it has gravitational potential energy, and it is 2 meters above the lowest point in the problem. The radius of the circle is 1 meter, so it is 2 meters above that. Is the object pressed up against some spring or piece of elastic at the top of the loop? I see no spring. I see no elastic, and Mr. Shelton didn't say anything about it, so no. Now this one's harder. Is the object moving there? Well, before you just say, yeah, I'm sure it is, there's another way to think about it. This is all the energy I had at the start. So far, it looks like I have less energy here, don't I? mg times 3 is more than mg times 2. That suggests there's some extra energy I still have to account for. If there's extra energy, it has to go somewhere. So it's very likely that the object is moving, because that's the only other form of energy we have. Now, all I have to do is set the 2 states equal to each other. That's it. That's how you do these. So I know I can't just say that and walk away, because it has not been the MO of this class. Now, I did give you the mass of the car, but I still have a substantial number of people who can't figure out whether they're allowed to cancel out the M's or not. In my last class period, I had somebody do this. Well, because both of those were in the mg term, so they canceled those M's out, but not the other M. And I know you exist in this room. The person doesn't understand this. In order to cancel out a term from both sides, every term must have the thing you're canceling out. And it has to be a non-zero term. Is there an m in every term on this side? There is. Is there an m in every term on this side? There is. So I can cancel the m's out in this instance. So I get that v equals the square root of 20, or 4.5 meters per second. You should be able to do the other two. They're exactly the same kind of work. Ask the same questions. I put nothing special there. This is not the level I need you working at. This is well below the level. So get A and C. Get them perfect. And if you don't, you should ask. If you don't ask, that's on you. Tomorrow we'll maybe have a quiz to see how you're doing on it. That should be a good way to turn up the level of concern. Not to be mean, just see if you can do a problem like this. All right, the two answers are on the board. Check yours. You should get the same thing. If you don't, you need help. All right. Now, we have limits on how much time I have today. But like I said, we're not actually at the level I need you to be at. This is just kind of the basics. So let me remind you that you're supposed to know other things. For example, and I would really strongly encourage you to stop what you're doing and deal with this. For example, we know that there are conditions necessary for the car to successfully make it to this point in the ride and keep traveling in a circle. We've covered that unit already. The question is, are we going fast enough when we're there at 4.5 meters per second to successfully make it through the circle? We've talked about problems like this. This is not an energy problem. This is a net force equals MAC problem. We're only successfully able to make it through the loop if these things balance. We know the speed, so we could find the right side. Right? mv squared over r. I wrote m 0.5, v 4.5 squared divided by r, the radius of curvature of the circle. But I also know that there's weight downwards and possibly a normal force downwards. We're only successfully able to make it through the turn if there's enough downward force to balance what's necessary for the centripetal acceleration. The limit for this example is when the normal force goes to 0. Work it out. If you get a normal force, you're doing fine. If your normal force is 0, you're okay. If your normal force is negative, you got troubles. That means the only way you make it safely through is if the track pulls up on the car. Can't do that. So you can find it out, though. Oops, I did my math wrong. Nobody said anything good. Nobody noticed. There. Now my math is done right. Now, I see 10 minus 5. Is that what you see? We got the 4.5 by taking the square root of 20. So 0.5 times 20 is 10. And mg is just 0.5 times 10. So this comes out to be 5 newtons. And it's positive. which means we're good. The car can successfully make it through the loop under these conditions. Our problems are going to have all of this stuff in it. Maybe not on a semester exam, but on our actual tests, yeah. All right, I have some frictionless track. Stick with that theme for now. Now our frictionless track, bless you, has a curve in it with a radius of curvature of 0.5 meters. I drop the block so that it falls right onto the track, smoothly transitions to this portion of the track, and then eventually comes to rest against the spring before being pushed backwards. Right, so there's a brief instant where the box stops against the spring. This would be the maximum compression of the spring, by the way. Because the block wasn't stopped, it would keep compressing the spring more. So the question for you is, what is the speed of the block here? And how far does it compress the spring here? Not much different. It's still a conservation of energy question. I give you the radius of curvature of the track. It's a distractor. Focus. The states of the problem are here and here. And this is the start of the problem. So compare those states together. You put the answer on here in just a minute. You just need this practice. These problems are not hard. They just take a little practice. They can get hard. These are not they. All right, the answers are up there. So in case I didn't detail this at the beginning of class, I thought I had, but I might have been thinking about first period. Elastic potential energy, 1/2 k x squared. The k is the spring constant. It's how difficult it is to compress or pull on your spring. So the bigger the spring constant, the harder it is to stretch out that spring. So think, a thick rubber band versus a thin rubber band. A thick one would have a higher spring constant. It takes more force to distort it. X is just how much you stretch or compress the spring to distance. So I gave you the spring constant here. I'm asking for how much the spring is compressed. One of the things I want to point out is that in a problem that has the spring constant, the mass won't cancel out. That's something that is new for this example. You're able to cancel it out here, the mass I mean, and we didn't need it at all in the prior example. But at the start, all we have is gravitational potential energy. At part B, all we have is elastic potential energy. You'll notice you'll need the mass. And any problem where there is a spring, you'll likely need the mass of the object. Still not terrible. You do have to know what K and know what X are. That's true. And hopefully you found that X is just a square root of 0.1.